So I'm going to walk through here the proofs of part A and B, and your job for homework is going to be to prove parts C and D. And so C and D work pretty similarly to the way A and B do. So just know that if you really understand this, you can probably do C and D. All right, so what we have here is we have 4 points in the plane that have an order. And I'm going to show that having an order means that some of these points are on the line defined by some of these other points. So in particular, we're going to prove that these ones in the middle are on the segment with the endpoints A and D. So, and that shouldn't be surprising because our definition for order is a lot like our definition of a line segment. So that's the first place we start. We start, your theorem proof always starts with what you know. So often you're going to even restate it. So if I was going to restate it, I would just say that I am given all of those ifs. And then once I have those givens written down exactly as it is in the theorem, I want to unpack that given. And so what I'm going to do is I'm going to write down the equation that I get from having the definition of an order. Now, what I want to get is I want to get that B is on AD. So I want to have an equation that has AB and BD and AD. And I don't want to have C in this equation. So I somehow have to get rid of the C. And so what I end up doing is I end up doing this equation that I can say about BC and CD that's just the triangle inequality. So this doesn't take the definition of a line at all. Just because there are any 3 points in the plane, I can write this down as an inequality. B to C and then C to D cannot be shorter than going from B to D. It is at least as long as going from B to D. All right, so how does that relate to this equation up here? Well, I have, let me grab a pen here. So I have here BC plus CD, and that's plus AB. So if I add AB to both sides of that inequality, then I get the next inequality. Right? So I add AB to both sides and I get this inequality. All right, now the thing you should notice is that the left-hand side of this inequality is the same as the left-hand side of this order equation. And so I can substitute AD in for AB plus BC plus CD. So here I go. There's my substitution. So I have this new equation, and notice this new equation, this new inequality has something in common with the one I want. So I want to prove that B is on AD. And to do that, I have to prove that AB plus BD is equal to AD. So I have part of that. I have AB plus BD, and I've shown that it is less than or equal to AD. So I'm part way there. But also, if I just forget that A, B, and D might have something to do with a line, and I just use the triangle inequality that says if I go from A to B and then from B to D, I can't possibly get there any faster than if I go straight from A to D. So right now I have AB plus BD, distance from A to B plus the distance from B to D. That is both less than or equal to and greater than or equal to the distance from A to D. Now if you've got two numbers, x and y, and you know that x is less than or equal to y and y is less than or equal to x, the only way that can happen is if those two numbers are equal. So I can say, because I have those inequalities going both ways, that I actually have an equation. And that equation is the definition of being on a line segment. And at the end I have written QED, which stands for the Latin quod eratus demonstrandum, which I'm probably saying wrong. I never took Latin. But it means that which was to be demonstrated. So I have gotten to the end and I've proved the thing I'm supposed to prove. Now, I put these in order, in a particular order that I think is going to make it easier to solve the problems. So I first showed that B was on AD, and I'm going to use that to show that C is on BD. And I think that if you first show that C is on AD, it will make it easier to show that B is on AC. Okay, so I recommend doing it in this order. All right, so here's my order again. Intuition, and then we'll start proving stuff. So here's my order: A, B, C, D. So I expect B to be on the segment from A to C. And I also expect C to be on the segment from B to D. And what I'm going to do is I'm going to use this equation that I just proved in part A to prove part B. So here's my equation from part A. And here is my definition of A, B, C, D being in order. So I just copied down that same equation from up on this line. And then I'm going to make a substitution. So let's think before we look at the next line, what would the substitution be? If all you knew was that it was going to be a substitution and you weren't looking ahead, you would say, let's looky here. You could also call it the transitive property of equality if you wanted. Looky here, I have AD in both equations. I could set them equal to each other because they're both equal to the distance from A to D. Looky here, I have them written down, they're equal to each other because they're both equal to the distance from A to D. Alright, so now, when I just look at those as equations, oops, I want to make another line break here. There we go. So if I just look at those as equations, I can see, check it out, I have an AB on both sides. I have AB on the left, and I have AB on the right. I could just subtract that from both sides, and I would be left with BC plus CD equals BD. Oh, you know what? That's exactly the definition that I need to show that C is on the segment B from B to D.